Okay, let's take a look at this system that has a fixed end, perfectly rigid at the left end, and a roller over at the right, where it's free to move left and right. It is free to be able to rotate at that specific point, at least free from an external standpoint, and it is completely restrained from being able to move up and down, hence the whole meaning of the roller. Now let's talk about how we can begin to estimate what these reactions are at the support using what we might call informed speculation. Right? We'll assume here that we've got elastic behavior at work, and we will also assume that we have constant EI in the beam, and should it not be that way, then we got to think about this a little bit differently. But for now, that is a fairly reasonable scenario given what we see in this beam, that it looks like it's constant depth or height all the way across this length. Right? So let's talk about how we might approach this from our first guess, which is let's just change this to a much simpler model. That is, now we've got a simply supported beam, no rotational restraint today. We've got the load W, and of course the reactions will split evenly, WL over 2, WL over 2 on either side. The other thing that we might do is look at a fixed beam. Now, interestingly, if we do that, the vertical reactions would be WL over 2 in both cases for this symmetrically loaded situation and symmetric structure. We look this up in a beam table with a fixed end moments or fixed beam, and we get WL squared over 12 and a negative sense on the left end, and also a WL squared over 12 and the negative or frowny face sense on the right hand side. Right? So there's your major difference, is that the moment reactions are different. Of course, in the first one, we have absolutely zero moment at the ends, and in the second, we get a WL squared over 12. Now, the moments variation along the length of the beam will still be second order. It'll turn out that the max positive moment on the left one would be WL squared over 8, whereas over here on the one on the right, our max positive moment would turn out to be positive WL squared over 24. Both will have second order variation here on these. Now, we could get misled here and think that the final vertical reaction, see, we did two extremes and we ended up with WL over 2 in both cases, so therefore that must be the reaction at A and the reaction at B, but that's not going to actually turn out to be the case at all. This asymmetry is what's going to cause that to change. For the moment at the left side, we know that the moment at A is going to be somewhere between 0 and the sort of worst case of ultimate sort of end rigidity or stiffness in terms of the supports. So this one on the end, maybe we guess that is somewhere in the middle between the two, your W squared over 24. And without knowing anything better, we might just go ahead and say, hey, we'll let the reaction be estimated as W over 2 is not going to turn out to be that way because of this asymmetry we've got in the foundations, even though the load and the beam itself are symmetric. Right? Now, there's our basic assumptions, and here's the beginning of how we've gotten there. The rationale here is that somehow the real situation is in between the two extreme models. However, not for all possible performance quantities, meaning the reactions or the max shears and moments or the maximum deflections. But certainly from the standpoint of the left moment, we know that that's going to be somewhere between the 0 and WL squared over 12. That restraining the moment over here at the right in the model that we did here isn't going to make this go any bigger than what we've already got with our two extremes. On the other hand, we know that the final moment, internal moment at B, is absolutely going to be 0 every single time. So that's why we don't have that one written down. Right? The vertical reaction at A is likely to be larger than WL over 2 due to asymmetry. One of the things that we're going to learn is that when you have indeterminate systems like we have here, that the load effects will tend to get sucked over to the more stiff part of the system, which is over here at A.